This here is the Arduino Uno. It is a development board we're using for this classroom. It is the USB interface between your computer and the microprocessor. It is the voltage regulator, the programming interface. It is the support structure for this processor. This here is the AT Mega 328. By far, it is the single most popular microcontroller on the market. Has been for 15-20 years. If you plug this into Google, you will find a ridiculous amount of information on it. Same thing with the Arduino Uno. The Arduino Uno is the simplified interface for learning how to program microcontrollers. Anywhere between high schools to colleges to universities, the Arduino Uno is just the default for learning it. You are learning this chip, but using the support structure, you don't have to learn how to regulate voltage. You don't have to worry about wiring up an interface. You don't have to worry about figuring out which pin is which. It's all labeled, all nice and neat in a uniform package. So this is the support for this processor. Now the Arduino Uno has a great number of features. Expanded from the microcontroller. On this side here we have 0 to 13, and these are digital pins. The digital pins can be inputs or outputs, and they operate at 5 volts or 0 volts. So digital high, 5 volts, digital low, 0 volts. They can be set as inputs or outputs. So unlike the chips you used, the 7400 series, 74000 series chips you used in Logic 1 and 2, every pin can be configured as an input or an output. There's nothing really stopping you. You just wire it up as you want and select if it's an input or an output. Some of these pins also have a little tilde in front of them. So pin 11 would have this in front of it, so it's tilde. This means pulse width modulation, PWM. So it generates a frequency. And you adjust the duty cycle. So duty cycle. So if you had a duty cycle of 50%, that means it's on half the time and off half the time. Pretty much even. This would give, if you hooked an LED up to that, it would be about 50% brightness. If you set the duty cycle to 90%, where it's on 90% of the time and then off maybe 10% of the time, it would appear as 90% brightness. The frequency is so high that your eye doesn't catch it, but it is actually turning on and off. This is how we can get an approximation of an analog value using digital, instead of, turning the voltage down to whatever voltage would represent 90% brightness. We can just turn the time down. We turn the time down a little bit, so you cut off 10% of the cycle. It's exactly the same to your eyeball. Now, that's not to say that other processors or digital devices wouldn't be able to actually see that. They would know that there's a pulse train here. But if you're dimming an LED or driving, say, a motor, you can drive it with pulse width modulation without ever having to actually adjust voltage or adjust resistance or adjust current. It's just adjusting the amount of time that it's on. On the left side, we have A0 through A5, and these are analog pins. So they have an analog input. Analog input feature that allows them to read 0 to 5 volts. So these can actually read a value. So if you had a potentiometer, you'd be able to read the position of the potentiometer. If you had a light sensor, you'd be able to read how much light is hitting that sensor at any given time. Another thing is a thermistor, a resistor that changes resistance based on temperature. That's what a thermometer is. It's reading the voltage drop across the thermistor as 0 to 5 volts, and it can figure out the temperature based on that resistance. At the same time, these are also digital pins. They have the ability to become digital in or digital out. These don't have the pulse width modulation features in them, but you have enough on one side, and these have the specific feature of being analog. On the top here, we have things like 5 volts and ground and voltage input and another ground. These are things you just connect to your breadboard to power it. So if you want 5 volts for your breadboard, say you're using a digital chip and you need to power it, you'd be able to pull it off of this and put it to your breadboard's rails. USB interface, power, and then this here is a reset button. Relatively simple. If you plug the USB port in, it's already powered. It's taking power off of the USB line. It's only going to be 5 volts, and if you say you wanted to make a little RC car, you would need to use the power jack to power it, because you're not going to have a USB cable running all the way to your computer just to power an RC car. You'd want it to be remote. You would want it to not be tied down, so you connect a little battery pack here, and that's pretty common. This can take anywhere between 6 and 12 volts. If you put 12 volts to it, this little regular chip's going to get pretty toasty, but it will still operate. We have our programming interface. So program interface. You can use this to program the microprocessor, but this little device here is already made to work with your computer through a USB port, so it's pretty simple to work with. But if you wanted to program the microcontroller like a professional or like someone who's in an actual production environment, you would just connect a device to this that automatically has everything built in, where it just detects it, checks it, uploads, and then tests it. So this is a more advanced feature, but we'll be doing something similar to this when we get to the later weeks, because we will be taking one of these and putting them into the breadboard. It's not. We're going to leave the same chip in your Arduino, but exactly the same chip we're going to put into the breadboard. And just as if we were programming it with the program interface, we're going to be wiring it up, and we'll be able to upload code to this that'll run on its own without all the support structure. So you'll be able to have a circuit on a breadboard without having to have the Arduino Uno connected to it. It won't need all this on the side. It's just going to be in a breadboard. And this is an upcoming lab, something you'd be able to do with the Arduino. We have power and ground running to the breadboard. Once it's on the breadboard rails, we just tap in there. And then in this one, we have a bunch of the digital pins connected to a chip. Right. The microcontrollers you use, these are not official Arduino chips. They don't have the Arduino, or they're not official Arduino boards. They don't have the Arduino logo on them. But Arduino is an open source platform, which means anyone, for any reason, can make any of the boards using whatever designs they want. The only thing they can't do is put the logo on it, unless they get licensed through the Arduino company. Open source means every single thing about it is freely available. You can find the schematic for this. You can find all the programs that are running on the chip to interface with the USB port. You can find the programs running on the little microcontroller between it and the USB port. Everything is fully available. Open source is wonderful. It's just better in every way. If you want something to do something it's not supposed to, you can do it. It's not like a car where the software is licensed and locked down with no ability to modify. It's open source. You can modify it at your will. One of the great things about it being open source is that standards have been developed over the years for it without having to license or pay a company for doing so. So things like Arduino shields with pins that exactly match the footprint of the Arduino are designed and available. I mean, they're ridiculously cheap. You get them from China or from SparkFun or whatever you want. Some have motor controllers. Some have breadboards for interfacing. And there's even ones for the more advanced Arduinos, like the Arduino Mega, that have everything you could possibly need to interface a 3D printer with the microcontroller. So it can completely control it, control the motors, read the sensors, everything. And it's always built into this simple little shield. You might see these on eBay, and they're just the whole point of a shield that you're buying pre-made is so that people that never took computer electronics technology or something like that could interface things without having to understand anything about AC or DC or capacitors or resistors. All of that just gets blown out of the water, and all you have to do is work on programming. So shields are made to simplify development for the microcontroller. You want to learn the microcontroller, you want to learn how to program it without having to learn anything else with it. You just happen to understand, you know there's a breadboard, you know how to wire things up because you've taken the degree. You may have seen other development boards like the Raspberry Pi. They are pretty popular, nowhere near as popular as Arduino, but they're gaining traction because this has a operating system. So while this Arduino processor only runs the program you put on it, it doesn't run anything in the background, it doesn't need anything supporting it, it doesn't need an operating system or a screen or an interface. This runs Linux usually, and so Linux is running in the background, and all of the programs you write are running through the kernel on top of that operating system, so that this is essentially a real computer. It's a full computer. It has video outputs. It has USB ports on the side. It's got Ethernet for connectivity. You can connect it with Wi-Fi. This here is an LCD header, and for the most part, it operates exactly the same as the Arduino, where you have a USB interface. You can power it with. You can upload code, but you can actually just connect a keyboard and mouse and operate this as if it's itself. So instead of using a Windows computer to interface, you could actually run this as a desktop running your code. It has a few pins, not as many as the Arduino, or not as full features as the Arduino, but it has pins on the outside which can control logic devices. This is actually a 3.3 volt device, so you wouldn't want to, rely on your digital chips working at that were designed for 5 volts working at 3.3 volts, but there are interfaces for it. All right, lastly, I'd like to go over some of the peripheral devices available in your kit. You could fill an entire room with just all the things that are available and designed for the Arduino. If you threw the term Arduino into eBay or Amazon, you would find millions of devices, all designed to be interfaced with the Arduino. But the ones in your kit are the more common. The ones for learning, they're cheap, and they're pretty much universal. You can use them in a lot of projects. First off, I want to do the servo motor. This is a little motor and a little gearbox and a controller. So you adjust the duty cycle on one of these pins, and it matches that with the angle of the shaft. So the shaft will turn to whatever you selected. So if you set a 50% duty cycle, the shaft will turn to 50%. So halfway between all the way to the right, all the way to the left, it will meet that automatically. So it doesn't matter what load is on it, doesn't matter where it was to begin with, it will just move to that position. These were pretty common back in the day for RC cars. If you wanted to control an RC car with an Arduino or any controller really, you would use this for the steering wheel. So to be able to turn the steering left and right, you would use a servo motor, just pulling the wheels in the front, either left or right. All right. Second, this is something you should already be familiar with from digital. 7-segment displays. You're just driving a bunch of segments all at once. Pretty much the simplest way to put out numerical data. You can also do a few letters with them. These are becoming obsolete, but only because displays have become so ridiculously cheap. So yeah, it's hard to beat the cost of just a couple dozen LEDs where this device here might be 10 cents. But if you can have a full graphic display, 128 by 64, you're gonna prefer it for most projects. So this is a little OLED display. This little protective cover on it right now. We'll pull them off when we do the lab. Just 4 lines, 4 pins to connect to it, power, ground, and 2 for data. This is a full display. You can even get these in full color. It's pretty much an identical screen to what is in your cell phone, where these are actually the cutoffs. The reason why these are so cheap is because of the cutoffs from cell phone manufacturing. So they'll manufacture sheets of OLED displays that are massive, and whatever is at the very end they can cut off and sell as little modules like this. They just connect a ribbon cable to it. But it's an actual display, just like a cell phone, where it's LED in the background. Or it's not LCD, it's LED, so every single individual pixel is lit. This is going to be one of the more fun labs where we can read data from it. There's a bunch of different displays, and there's a few in your kits, but this is by far my favorite. This here, you see these on Arduino projects. So if you Googled Arduino robot, this is what you would probably see right on the front, right on the top. And a lot of kits add these just because they look like eyeballs. It'll make a robot look more realistic, like a Android. But these are actually distance sensors. So one of them is creating a pulse, and the other one is receiving the pulse. So if it bounces off of something, the amount of time it takes to travel through the air, bounce off it, and travel back, this device will let the Arduino know how long that was. With a few calculations, you can figure out what that distance is, and more or less, you can create a robot that knows when it's about to collide with something. You see these on little robotic vacuums. You see them on pretty much every robotic project that you'd find on YouTube. They are very good at what they do. They're not going to be able to. It's not like a full camera system where a camera has to process all the information and know how to respond to the environment. This is just distance sensing, a little bit easier to work with. This here is a humidity sensor. You can find tons of gas sensors all over eBay. There are sensors that are for alcohol, like a breathalyzer. There are ones that even work the same as smoke alarms. And for a few dollars, you can add any kind of sensor you want. There's ones that will sense conductivity through soil to know how much water's in the soil. pH sensors. There's anything you could possibly imagine. Probably going to exist as a little module like this, because this little chip here is probably 10 cents, and they add a little PCB to it with some LEDs, so you can really know what's going on, and then a little interface for the Arduino plugs right in. Unlike the servo motor, this is a stepper motor. You can control very precisely the angle it's turning, but it'll be able to turn all the way. So if you want to turn the motor 50 times, so let's say it's an RC car and you want to be able to very precisely move a certain distance. If you just put power to a normal motor, it's just going to go, and then if you stop, it might stop where it's supposed to stop, it might not. With this, you get very precise control. These are used in 3D printers for that reason. You can very precisely move the print head or move the bed or advance filament, whatever it happens to be, through a digital motor. It's quite literally what a digital motor is. It comes with this little interface because this is a very powerful motor compared to what the Arduino is used to. The Arduino is not going to put a lot of current out, so it's got a little controller you work with it. This here is a infrared transceiver. It's actually set up as an infrared receiver for the remote, but it can work with any kind of remote, garage door remotes that are infrared, TV remotes. I even have one of these in the bedroom to control the air conditioner, so I can tell Google to turn the air conditioner off. So Google tells if tells one of my microcontrollers, and one of my microcontrollers pulses out the off code for the air conditioner, so it just turns it off. So you don't have to get up and walk across the room. With this, you could do a lot of things. Obviously, it's set up for as if it's for an audio device where you got channels, you got playback and numbers, but there's no reason not to map these to directional keys. You control something remotely, whatever you happen to be. So this is a neat little thing. Don't pull out the little tab for the battery yet. It's from China, so I have no idea if that battery is going to last the whole semester. If you do go to use projects in the future, just get a good one. Don't just buy from China. And then lastly, this is a device that probably everyone recognizes. It is a joystick, the same exact joystick you see in game controllers for Xbox, PlayStation, whatever. You have X-axis and you have Y-axis control. They are just potentiometers. So the potentiometer turns as the joystick turns. So you have X and Y-axis. And as simple as that, you're just reading the analog voltage from the potentiometer's wiper. So it's no different than having a potentiometer that you turn the knob. It exists the same way. And on the front here we have these 5 pins. So 2 for power, that's just 5 volts and ground. And then we have the wipers from the potentiometers to know the X position and the Y position. And last, we also have one for the button. I don't know if you can hear that, but it's a clicking button. So it's just a little button on there because these modules do come from the same exact factories that make, I think these are the PlayStation ones. So the PlayStation, newer PlayStation controllers. Yeah,